Okay, welcome to our seminar and thanks for showing up after the snowstorm. And today we are very glad to have our invited guest actually from Hawaii. And he could bring us some sunshine and to us, I hope. So Dr. James Saal is the Director of External Research Programs at Citrine Informatics, and where he managed Citrine's government-funded research programs, advancing the state-of-the-art in materials informatics and with academic, government, and industrial collaboration. So today you expect to hear a lot of how we can use, how the company use like a machine learning, data science, technology, and in material design. So I think this is a pretty hot topic now in our community. And before joining Citrix in the 2018, James was manager of technology at Questech, right? Yes, yeah, okay. Innovations and leading programs in alloy design and ICME methods. So ICME stands for Integrated Computational Material Engineering. So most likely it's like multi-scale modeling techniques and everything combined together to lead to advanced material design. So that's called ICME method development. Dr. Saal earned his bachelor degree in material science and engineering from Rice University in 2005, and he's a PhD in material science and engineering from the Pennsylvania State University in 2010, where he focused on the integration of density functional theory with the CalFET for material design. And he continued postdoc study at Northwestern University, developing a high throughput material property database and studying magnesium and cobalt-based alloys. And since then, and Dr. Saal has specialized in computational simulation of process structure property relationships, ICME design of a new material, and the use of data-driven methods in material science. His research has included alloy, ceramics, and polymers, and diverse properties such as corrosion and the addictive manufacturing, printabilities, and thermoelectric performance. Dr. Saal is the author of over 50 peer-reviewed publications, several patents on design material, and a co-edited book on computational material system design. And he has served as a trustee of ASM International and chair of the TMS ICME committee. So no further delay, and that's yours.
All right, thank you. Okay. Yep, it's working. Great. Well, thank you so much, Lon, and for the introduction and, of course, the invitation. I'm really happy to be here. Lon and I go way back, so it's nice to see her neck of the woods. Yeah, I am the Director of External Research at Citrine Informatics. I'll talk a little bit about what that means. But just one in addition to my background is my background is primarily in metallurgy, and I've got a lot of experience in a variety of different problems and a variety of different applications for materials, computational materials and materials design. But metallurgy and phase diagrams and thermodynamics was my first love. So a lot of my examples I tend to talk to ad hoc kind of come from that realm. So I'm going to talk about the kind of work that my group does, some of the larger ideas around machine learning and AI and materials. But I usually like to start by, by giving some context for the work. As a material scientist, we're striving for advancing, accelerating the development of new materials and bringing new materials to applications and making an impact on society. At a very high level, there was the Materials Genome Initiative back in 2011 that was funded by the Obama administration to try to accelerate materials design and materials development. Well, 10 years after the beginning of the Materials Genome Initiative, the MGI, they refocused. And as a community, they identified 3 primary goals for the material science community to try to accelerate and improve the impact of our collective efforts in understanding materials. And those 3 primary goals included unifying our materials innovation infrastructure, which means trying to get everybody on the same page in terms of putting data together, putting tools together, putting experiments together in ways that are collectively improving our understanding of materials very broadly, and some kind of a unified infrastructure. The second is doing a better job of trying to harness materials data, generating materials data and understanding materials data. And the third is education, training, and basically getting people up to speed on the latest and greatest and what's going on within the workforce. And I like to throw this up because I'd like to think that our goals at Citrine tend to work towards all three of these pillars within the MGI. So I'm going to talk today about a couple different things. First is what the heck is Citrine? I'll put my business hat on and talk about the elevator pitch for the company. I'll talk about some commercial use cases for AI ML within our portfolio of customers that we're able to actually disclose. And then I'll talk a bit more about the work that I've been doing with my group on academic use cases, working with universities and national labs and government-funded programs, and then some conclusions. So a little bit about Citrine. We are a company that does AI and machine learning for materials and chemicals. We're developing tools to help other organizations like Boise State or like 3M or like Pacific Northwest National Lab or Idaho National Lab to do these kind of calculations and analysis at scale. So we provide basically machine learning and AI for materials and chemicals as a software as a service or SaaS platform. And the idea is that can we use the experts within organizations and the expertise within organizations to accelerate product development by giving them the tools to be able to do these kind of informatics tasks basically as part of their day-to-day projects. And so what are the impacts for using AI ML within materials and chemistry? Developing better, more sustainable products, developing products faster, improving supply chain resiliency. If a chemical suddenly we understand to be toxic, like PFAS, how do we very quickly reformulate things in order to improve performance, but while also acknowledging regulatory restrictions. Reduction in COGS, which is basically the cost of actually manufacturing and producing materials, and then being faster, more responsive to customers. So this is the industrial case or business case for why we exist and why we're trying to sell to companies, because these are the benefits of using these kind of tools for materials and chemicals development. What exactly is the software that we have? Well, it basically consists of 4 components. Materials Informatics, essentially, it consists of these as well. So we're basically developing a workflow for doing materials and chemicals informatics and generalizing that across different problems, including the development of data sets or the management of data and materials data, the building of machine learning models on that data, defining search spaces. So what is the composition range you want to optimize within, or what is the manufacturing process parameter range you want to try to optimize within, and defining those, and then developing candidates. So using the machine learning models, what are materials or chemicals that are likely in order to be able to hit some kind of performance metric that you're just saying, like, I want something that's high toughness and high strength, while also being cheap to make or manufacturable. And then basically you do those experiments, and those experiments are then back in the data, and then you repeat this kind of workflow loop here. And that is our Citrine platform in a nutshell. And these are just some screenshots to show that it's a real software. It exists. It's based on the web, and we use a web GUI in order to be able to access it, and has a Python API and all that fun stuff. And here's a bunch of customers and collaborators of ours. They range in size from being small to big companies, and also academic and government labs. And this is just meant to show, hey, we do a bunch of stuff on different types of problems: formulations, polymers, composites, glasses, metals and alloys, and functional materials, amongst other things. So talking a bit more about methods, this idea of iteratively training a model, making a prediction, and then doing an experiment and feeding the data back into the model. The community calls it active learning. We have a method of doing it called sequential learning. The idea is that you do this kind of iterative loop, and this is the quickest, most efficient way of trying to achieve some kind of a performance metric with an experimental budget to develop a new product. So you have a machine learning model, you predict what material you want to measure next, you run the experiment, and those results back to the data set, update your model. It's kind of the scientific method, essentially, in this loop, but we're just using a machine learning model as part of it. A lot of the secret sauce, if you will, about the magic happens within this predict which material to measure next. How do you predict that? How do you make a decision about what material to measure next? Well, here's a hypothetical situation. You're trying to predict fatigue strength of a metal alloy. You've got, I don't know, 50 candidates. that you could potentially do experiments on. These are new materials, haven't been made yet. These are model predictions of fatigue strength. And the error bars here correlate basically are the uncertainties of the prediction. This is the machine learning model's prediction of the uncertainties of its own predictions. So you can see some are really good, some have very small error bars, some are really bad. There's one that has a big honking error bar there. And then there's some in between. And so with this situation here, we want to hit this dashed line at the top, really high fatigue strength. What experiment should I run here based on this information? Well, you could do one tactic, which is just say, I want to choose the highest point on this list. It's the highest performing, therefore it's maybe my best shot on goal. It also has a small error bar, so I'm pretty certain I'm going to be able to hit that strength. It's not my target, but it's the best bet. That's called an exploitation strategy in machine learning parlance. Alternatively, you could say, actually, my model's not doing well. It's not doing great. I want to make the model better. So I'm going to choose this particular point here that's got the biggest error bar. Because if you do that data point, you do that experiment, you feed that data back into your model, that uncertainty, that error bar is going to collapse down to zero because now you've told it that. So you're basically teaching the model a lot about that one point. Maybe it's got a weird composition relative to the others, and the model just was a big extrapolative leap for the model to make a prediction on that point. So this is actually would be an exploration strategy, and that's a great way for teaching the model. Basically, if you want to make the model better, that's probably your best bet. So what we actually have developed is a couple of algorithms for choosing a hybrid approach where you want a good performance while also having a large-ish error bar, so that not only are you having a shot on goal to hitting some kind of performance metric, but you're also teaching the model something when you do it. So knowing that you're probably going to have to do this iterative loop a couple times, this is a good way of, at least in the beginning of your process, to make the model better while also having a shot on goal, basically. And so, maybe you want to be within 2 sigma of the value and that's actually pretty close to the dash line there. So this would be maybe a good candidate. So basically, our software does all this stuff behind the scenes for you to be able to tell you which experiments to run within some search space, and that's the gist of our process. So I'll skip this slide and go straight to commercial case study. So we've used this approach many times throughout all of our customers, and there's a couple that I'm actually able to talk about publicly. The first is a program with HRL Labs, which is a company over in Malibu, California, where they wanted to develop a high-strength aluminum alloy for aerospace applications. Well, the challenge is for additive manufacturing, high-strength aluminum tends to have a lot of problems with rapid solidification. It creates very weak, coarse-grained materials. So they had a notion, they wanted to bring in nanoparticles in addition to the powder in order to be able to improve the grain pinning performance during the solidification. And the challenge was there's a lot of things they could add to aluminum alloys to pin grains. What's the best thing, the most effective way of doing that? So coming up with a list of candidates was basically a very large task where we had a couple million candidates they could have added that are in equilibrium with various aluminum alloys, including 7075 or 6061. So we did an algorithmic search. We used our machine learning models. We helped them narrow down their candidates to about 100 instead of these 11.5 million. And a couple of these are shown there in the middle there. And you can see that we were able to take a fairly large space and whittle it down quite a bit so that by their metrics, we were able to take years of work down to a couple of days. And it worked. If you look at the paper down there at the bottom and from Nature, the winner was this one at the top, the top left there, the 7075 with titanium diboride. And it worked out pretty well. The first powder customer is NASA, and it's actually being in use right now. We had another program with the Colorado School of Mines and their TARDEC Center, which is the Tank Automotive Research Development Engineering Center, about making door hinges for armored vehicles. They were breaking out in the field. It's a big deal because if your door doesn't work and you're in a tank, you're exposed. And it would take up to 2 years to get the new tank to the field. It's a logistical nightmare. So the idea was, can we print something at the front lines and just throw that in there? So the challenge was figuring out what the optimum print parameters are for new alloys at the field based on what they would have available at hand and at the front lines. So we developed models to be able to predict for a given machine type, for a given powder type, what is the best parameters, your knobs to turn on your print machine so that you have the best performance, something that's good enough for a hinge. And we were able to do this pretty quickly with 84% accuracy on the first builds of these runs. So you don't have to waste a lot of time building a lot of test coupons first. You just go straight to building the part you need. So we were able to reduce the strength So reduce the weight and improve the strength of these hinges as well by doing topology optimization for these pieces. And so 24-hour fabrication delivery from 2 years is a pretty good improvement here. And then the last of these commercial applications is this program with a tool company where they wanted to improve mechanical performance of some coating technology that they were putting on top of their tools. And they thought that additive could help them with that. The problem was, of all things additive, it's a very complex manufacturing process. There's a lot of ways you could optimize things, a lot of knobs to turn, basically. And there was very time-consuming to test. Each one of these tests took a couple of weeks to do one set of build parameters, and you've got thousands to choose from. So before they met us, they weren't able to solve this problem. We used our Citrine platform to help them. Here's a timeline that shows the part that they had done in terms of doing kind of a traditional DOE, design of experiments process. You can see that a couple of years they were having some challenges of hitting all of their mechanical performance targets. But then they brought us into the process, and we were able to hit pretty quickly what they wanted to do, all 4 of these design metrics. So on the right there, you can see that we were able to basically achieve this with significantly reduced time and effort in terms of testing. So these are the examples. One last example is just an integration with multi-scale models with Siemens. You can imagine that this AI/ML engine is a good component of much larger workflows of models, multi-scale models in particular. In this case, looking at fibers in a polymer matrix and trying to look at multi-scale behaviors and optimizing the materials performance of the individual ingredients here. In this case, the matrix and the fibers, and coming up with optimum formulations that can then go to physical testing, but doing this all with an integrated simulation workflow. So, okay. That was a lot, but I wanted to get through those because those are the ones I'm not allowed to talk about in any great detail because there are commercial applications. There are quite a few, though, that I am able to go into much detail, and I have personal exposure to as well because my group did it. But basically, I lead the group that's the external research department. And what that means is we basically the government research group. So, yes, Eric.
He was an RE student here at Boise State.
I did not know that. Why didn't he tell me that? He knew I was coming here. Well, there you go. So we choose the best and the brightest in my group. Basically, yeah, Kyle's one of our new hires from last year. We basically go after and work on government research for the focus of making publishable case studies that show off that this AI/ML stuff is worthwhile and should be taken, should be considered. So we collaborate with universities, government labs, and industry. We have expertise on a bunch of different things, but particularly with regards to atomistic simulations, like Kyle, for instance, and myself, but also developing open source and web development tools for supporting materials research and doing education, and a bunch of logos, a bunch of collaborators. I just submitted a proposal with Lon and some other folks, so I hope to add Boise's logo to this pretty soon. That's what I basically do for a living. And so for the next couple of slides here, and really for the remainder of the talk, I want to go into a lot more detail about some of the stuff that we've done. And hopefully that should be some good fodder for a conversation later. So the first is a program that we have with Panasonic. This is actually one of the few non-government funded stuff that my group has done. But this is with on the goal of developing organic semiconductors. And so the idea was to combine AI and simulations to identify new organic molecules that are good applications for printable RFID devices. And this requires basically good semiconductors, which boils down to good, a particular quirk of hole mobilities, or the electron holes going through some of these molecules. And so the idea was they had the latest and greatest version of probably Gaussian or something like that would do the time-dependent DFT on these molecules and predict the hole mobility for these molecules, the critical property that we needed for this application. But it would literally take a full week of CPU time in order to actually, well, it was actually real time, so who knows how much CPU time was necessary. But it took them a week to get an actual calculation done. So there are millions of potential possibilities here with regard to small molecules that could be candidate materials here, but you can't do 1 week calculations on a million molecules. That'd be too much. So what we did is the right half of this workflow was to basically train a machine learning model to be a surrogate for the expensive DFT. And so our experiment, quote unquote, is the DFT. How well can we make a model to basically reproduce the DFT and then identify within the hundreds of millions of molecules that are candidates, what are the best ones to do DFT on. And then we just iterate on this until we come up with something that's good. So this is the plot here that shows how we filtered it down from billions of molecules, 500,000 compounds that we probably thought were the best ones based on a variety of metrics. We started with only about 30 calculations from their DFT, and we ended up only having to do 200-ish total before we found the good candidate materials that they actually went ahead and started patenting. All the gory details are down there in the paper on the bottom, but I can show you the key figures here from that paper. The plot on the left shows off basically this sequential learning process of the iteration number at the bottom there, and on the left is the metric is just the whole mobility itself. And so the higher the better for whole mobilities. And what you're basically seeing are a bunch of lines that describe the performance of our sequential learning process and our ability to hit these marks over the course of these iterations. And so the blue line corresponds to the best whole mobility period that we have available to us at the time. So our training data had one that was pretty high. That's why it starts so flat, because we weren't able to find anything better than it until like halfway through this process. The orange line corresponds to the best thing that the machine learning model and this DFT has found within the program itself. So we were able to start pretty low, as you can see, pretty close to 0, but then we were getting better and better until we hit like this wall at about iteration 6 or so. And I'll get into some detail about why that was. But then each of the points corresponds to a given iteration. These were the calculations that Panasonic ended up doing as part of their DFT. So the change that really made a big effect wasn't so much that we switched some hyperparameter in the formula of how we were doing the selection strategy. We weren't going from exploitation to exploration or anything like that, although we were playing around with that early on. The dashed line that's gray vertical is the custom design space. We were actually switched from a very small, very focused set of possible molecules that we were choosing from, things that people had tried in the past for electronic applications. We switched to a much broader space of all known molecules. And once we got a little crazier with that, then the machine learning model started to predict a lot more diverse sets of molecules to test. That's when we kind of got outside of a local minima, if you will, about where people have already looked for these kind of things and found something really novel. Because the machine learning model is somewhat cheap to run, we could run it on an order of magnitude more molecules without much effort. And so once we did that, that's when, after about 10 iterations or so, we were able to find something that was significantly better than anything they had seen before. And in fact, it was pretty interesting. So if you look on the right, we were able to find this particular class of molecules called thionoacenes. I can't pronounce that, but it has about 25% higher whole mobility than anything we had found before. And what was interesting was that nobody had ever thought to look at this class of molecules for this kind of particular property. But when they did their DFT, it validated that. The experiment, quote unquote, validated that. And people knew how to make this. So it wasn't necessarily something out of left field. So this was really actually a pretty interesting result, because it gave them new insights into how to design these things in reality. There was some interesting new possibilities here. So this was a pretty interesting result for us. And the fact that we got patents out of it as well, that they got patents out of it as well, was the icing on the cake there. Okay, so this is a program that was funded by the Department of Energy with SLAC, and SLAC is the national lab, the DOE national lab based out of Stanford. And we had a challenge here where they were developing these nanoparticle catalysts, and they were trying to manufacture them in a pretty robust way. The challenge is there's a lot of these, again, knobs to turn in your reactors when you're manufacturing nanoparticles. And in order to be able to characterize these nanoparticles to see, did you get the thing you actually wanted? Did you get like a very tight amount of a particular particle at a particular size? They don't want a very broad size range of particles. They want almost a delta function in the particle range distribution, particle size distribution. They need to be able to actually do this kind of analysis within the beamline at SLAC. And I've never done beamline stuff, but I've heard from a lot of people who've done beamline stuff. You get like 2 days on this line, and then you're like living there. You got to use every single minute of that line, because you wait weeks or months in order to get access to this. So the challenge was they wanted to very rapidly test a set of knobs on these reactors, make the nanoparticles, characterize it, and then take the results of that characterization and immediately make more particles and do it again until they could figure out the optimum way of doing it. So they had to do all this stuff in real time while they had access to the beamline. And so that's exactly now where machine learning can help. So if you have, in this case, they had a couple different design space parameters that they were trying to optimize against: reactor temperature, the flow rate, and 3 different liquid reagents, so 5 dimensions. How can we very rapidly test this and assess what the optimum is within 2 days of this beamline access? Oops. So again, this is all published, but these are the figures that show, again, as a function of the experiment number, how did the sequential learning do in terms of finding this optimum. So these are 3 different metrics that they were trying to optimize simultaneously. And with our software and with most of these methods, you can do multi-parameter optimization. They were looking at the sigma, which was the particle size distribution. So the smaller that is, the narrower the distribution is, the closer it is to a delta function. The particle radius, you're trying to hit some kind of particular target size. And then the intensity, which is equivalent to the particle yield, and you want to minimize that. So the first couple of experiments were just initialization. You need some data to train a machine learning model. And so we took the first 16 of them just to be like a grid search to initialize the training set. And then we turned on sequential learning with a vertical red line there after the 16th experiment. And you can see very quickly it's able to latch on to making very small sigmas. It took a while to get to the target size, but we got there, and then minimizing the intensity there simultaneously. So this was an example of real-time machine learning in order to be able to do automated experimentation, which is a very, very, very compelling use case for AI ML right now, because a lot of people are trying to explore how do we automate self-driving labs and things like that. And machine learning and AI is unnecessary, in my opinion, basically brain in order to be driving these kind of labs. That's on the software side. All right, another example is alloy corrosion. So again, my background is in alloy, so this was a nice project to work on as part of a large EFRC with the Department of Energy in Ohio State. Alloy corrosion is very complex. There's a lot of phenomena that happen at the same time. They're all happening at the same time, and it's usually a weakest link argument about which mechanism is important. So when you do measurements of corrosion, there's also a lot of environmental considerations in terms of what temperature you're going to measure at, how much salt, what's your pH of the solution. So it becomes a very complex and messy set of parameters that feed into coming up with one measurement of a corrosion metric, of which there are actually at least 8 of them. So what nobody had done before is actually go in and scrape the literature, come up with a once coherent data set of alloy corrosion metrics for across different alloy classes. And so we did that as part of this project. And we came up with a machine learning ready data set to enable this kind of machine learning of this corrosion performance. So we looked at 85 publications, 4 materials classes, come up with over 1,000 data points. And the plot on the right is basically a summary of the data points, color-coded by what alloy class they are. And on the y-axis is one of these corrosion metrics, is the pitting potential. So it's the amount of electronic potential across the material in order to induce a pit within the surface of the material. And the x-axis is configurational entropy of the formula, which was meant to indicate how simple the alloy is versus how complex it is, because high entropy alloys, or HEAs, is one very common hot topic right now for the alloy community. But you can see that there are various aluminum alloys tend to be very pure or very low alloy, and then iron and nickel chrome moly type of alloys also tend to be kind of in the middle. So this is just meant to show off the range of the data and what the scale of this pitting potential looks like. But now we can actually design a corrosion-resistant alloy if we have a data set like this. So we worked with the EFRC, we made the data set, and we came up with like a hypothetical design goal of, I'll use the mouse here. So using our tools, we were able to, can we identify a steel with a superior corrosion performance to 316L, which is a very common, very widely used stainless steel at an equivalent or lower cost. So to do that, we developed a modeling workflow, a machine learning model architecture that had a bunch of inputs, in this case, temperature, and then the pH, the chloride concentration. So those are the measurement metadata, if you will, the conditions for your corrosion metric. Of course, composition as well as an input. And then we took a lot of CalFAT predictions. CalFAT is another kind of simulation tool that you can add on top of this to give information about the microstructure of these materials. So as we all know, microstructure is important for materials. So things like, what is the matrix phase? What is the composition of the matrix phase? Are there precipitates? If so, what percentage of the microstructure is made up of precipitates? Things like that. We also integrated DFT, which is an atomistic quantum mechanical-based system of simulating properties. In this case, things like surface energy, cohesive energy, band gap was on here. And then we also looked at PREN, which is a very simple rule of thumb kind of model for corrosion engineering that a lot of engineers use out in the field. And the idea was we could bring all this stuff together and put it all into one model in a way that maybe a human would require a lot of physical intuition or even a PhD thesis or two in order to be able to figure out how these models all interact with each other correctly. But with machine learning and an acknowledgement that we're just looking for the needle in the haystack, we're not necessarily looking for the complete story of how to get there. We can find the correlations between all this input data as quickly as possible using machine learning to find out what is a optimum output here. And then we also have a simple model for raw material cost, which is just basically the cost of the elements. So putting all this together, we were able to look at possible new corrosion-resistant steels, where on the plot here on the left corresponds to predictions of specific cost, so the cost per unit kilogram, and the pitting potential. And these are all novel alloys that we generated, and these are steels specifically, that we generated with just a simple generative model from Monte Carlo. And you can see 316L there at the pinpoint. And what you're looking for are things that are on the upper left for low cost, high performance. And you can see that there's actually quite a bit of possibility here for something that outperforms 316L. And so we actually started looking at some of these with our collaborators at Ohio State to maybe melt some and just test to see if they were agreeing with at least notionally with this experiment or this machine learning prediction. The plot on the right is interesting because with any of these kind of machine learning predictions, you want to understand: does it make physical sense? Is it consistent with my intuition or prior history with these materials? And so pitting potential is a very common metric for stainless steels. The higher, the better. That means it's more resistant to corrosion and exposure to water. And it's a very common rule of thumb with stainless steels that chromium is the secret sauce to making a stainless steel stainless. And that usually happens at around 10% weight percent of chromium. That's a very common metric that people use. You might have all seen this in your Material Science 101 textbook. Well, the data from these new alloys actually bears that out, where you can see beyond about 10%, the pitting potential increases quite a bit. So you're getting physically consistent behavior from this machine learning model to what we all kind of know from our material science backgrounds. So it's important to check these kind of things to make sure your machine learning model is giving you relevant and sane results. All right, another class of problems that we looked at were for electrochemical systems. In this case, working with RPE, which is basically the Department of Energy's DARPA, and Carnegie Mellon, on looking at systems for catalysts, in particular the Haber-Bosch process, catalysts and battery electrolytes. And the idea behind this program was, how can we utilize machine learning and other kind of scientific tools to automate as much as possible simulation and experiments to rapidly accelerate the development of materials within these two processes. And we actually wrote a paper, which is down there at the bottom for Automat, that tries to quantify this acceleration rate for problems related to DFT, for problems related to experiments, and the contributions from individual drivers for that acceleration, including machine learning and the kind of active learning we've been describing here. So, for almost any kind of application of machine learning to design, you're going to see this kind of iterative loop played out because it's pretty much standard at this point. This is the way to do these kind of processes. So Haber-Bosch is basically a problem with regards to catalysis about the generation of ammonia. And Haber-Bosch is actually responsible for 96% of ammonia throughout the world. And it supports about a third of global food production for 2.5 billion people. It's a very energy-intensive process, Haber-Bosch. And catalysis is basically the only way we have in order to be able to reduce the energy input for this process. So it consumes 5% of all global natural gas, 2% of all global energy for ammonia production, and is responsible for a big chunk of CO2 emissions. So that makes food essentially a fossil fuel derivative because we rely on fossil fuels so much in order to be able to perform this process. So there's a lot of work towards trying to create better catalysts for this particular application. And we worked with Carnegie Mellon on developing automated DFT pipelines accelerated with machine learning to be able to search for better catalysts for this nitrogen reduction reaction. So again, very similar to plots to what I showed before, but iteration count on the left and two different metrics for performance on this left plot. The first is AQ, which is the acquisition function, which takes into account the properties on the right, which I'll get to in a minute. And then the candidate predicted a model uncertainty on the right. So what we're basically showing is that not only are we getting closer to a better performing materials as we go down up an iteration count, but we're also reducing model uncertainty as we do it because we're using this kind of hybrid approach. So and I think that's an important point to make because if you want to try to find high-performing materials, you also need to be a bit explorative, a bit riskier in terms of trying to ascertain, where these needles in the haystack lie. And then on the right are just two of the metrics for performance that we were looking at for this project. The color coding here corresponds to the iteration count, so you can see how it evolves as a function of the sequential learning iteration. But this is the very common volcano plots you see in catalyst papers. This is the activity of the catalyst with regards to the process you care about. And on the x-axis is basically the free energy for the reaction that you're trying to catalyze. And you can see you want to be in this window here. And as we get closer to later in the iteration count, as the color gets redder, you get closer to the peak of that volcano, which is where you want to be. And on the right, we're looking at two different properties here. The y-axis is the segregation energy, which is a measure of the stability of the catalyst, which is obviously very important in terms of reusability of the catalyst and its ability to actually manufacture the thing. And on the x-axis is HHI, which is a metric for how expensive or how hard it is to secure the element within the distribution of manufacturing throughout the world. So a critical mineral like rhenium here is going to be, you can only source it in China, for instance. That's going to be something that's color coded as a high normalized HHI. Or low HHI, I should say. So what you want to be is on the right. So and that corresponds to cost and economics of the material. So the point here being that we're getting more economical and stable as we get further in the iteration count. Okay, and then the electrolytes were the other application that we looked at in this project, and so. Battery electrolytes are a very complex problem that a lot of people have been looking at for quite a long time. This plot here shows the Coulombic efficiency for electrolytes within batteries, and Coulombic efficiency is basically a measure for every time you charge and discharge the battery, how much of the original charge are you able to retain as a function of the percentage of the battery charge. So you want this to be as close to 100% as possible because you want to charge and discharge a lot. So anything less than 100 is probably going to significantly decrease your the amount of these times you can charge and discharge, which is a big problem if you want to try to commercialize any of these batteries. And the electrolyte is a big bottleneck for that. And you can see there's been a significant amount of work on trying to improve this from 80% down to 1974 or so, up to a couple nines of performance within this somewhat complex formulation there at the top right. So there's two interesting trends here. It's getting better over time, but it's also getting more complex over time. And that's a challenge when you're trying to discover new things, because that means additional complexity, additional more larger design spaces, and having to understand that and navigate that and come up with something good is difficult and enter machine learning, right? So the first thing we did was develop a machine learning model for molecular electronic properties. We grabbed a data set from the internet that people have already done this for a large range of large number of molecules. The QM9 data set in particular is a good one. And we need to make predictions for things like the HOMO and the LUMO for these molecules. And we defined some property thresholds based on our application here, in this case, specifically the stability against the lithium anode and some representative cathode. And we were able to narrow down in the training set the number of targets from a huge number to only 27. This is a sampling of the data set for the purposes of random forest training. There you go. And we were able to make some models for the good HOMO LUMO, basically. And this is against the entire data set. And you can see that we do a pretty good job of predicting within the range that we care about here pretty nicely. But that's the first step. Now that we've got a model, how do we generate new candidate materials? And that's difficult within the molecular world, because you can put balls and sticks together for molecules willy-nilly, but you don't know if you have a good one or not. You can create a lot of non-physical or completely non-synthesizable materials very easily. So how do you whittle down the billions of potential molecules, probably infinite, to something that makes sense and that is calculable and even synthesizable? So we went through, we made this large workflow here to try to find these lithium metal battery solvents. We basically took the good solvents in this first step. We found 30 that were known to be very good molecules, that basically the stuff from this plot. We broke it down into their constituent subcomponents, fragments, we call them, and there's a method called bricks for decomposing these molecules into these fragments. And then you take the fragments of the good molecules and you just recombine them like Legos into new molecules. And this kind of combinatorial assembly allows you to create a large pool of new molecules that you could probably, hopefully are going to have some character of the good stuff that you started with, while also having some novelty to them that are going to outperform the known things. Then using these new candidates, can we screen them based on various metrics we'll show in a minute for synthesizability, suitability, are these physical, using our Homo and Lumo models now to see if they're any good. And then taking this, now what is the final bit of screen candidates that are then can be used as part of a experimental study. So just walking through this process, here's the pool of good molecules that we've started with from that first plot. We broke it down into a bunch of fragments. So these are the constituent fragments that created these good solvents. And then we just combinatorially developed new ones, and this is just a sample of them. And then we screened them by going through how many of this over, let's say a couple hundred, 900 or so molecules have a HOMO less than 7.8, negative 7.8, a LUMO greater than 1. And then of these, we ran some very simple calculations and simulations on energetic calculations, like what are their total energies based on things like steric hindrance and whatnot. You can roll those out, or dangling bonds or things like that, and synthesizability. And then we ended up with a pool of about 59 that we were able to pass all these screens. And now we found basically the likely needle in the haystack with this process. And so we did do some experimental optimization of these electrolytes. So the challenge for the electrolytes is that it's not just the molecule, but it's the molecule plus a bunch of other stuff, salts that need to be mixed as well to optimize performance. And so this is where we then worked with a group at Carnegie Mellon who had an automated experimentation lab where we gave them basically the set of molecules that we wanted to look at. They took those molecules, they took these solvents and salts, and then they optimized within those using our machine learning models for performance. What are the best of these materials for the given molecule? What is the optimum electrolyte? And that's the thing you want to try to put on that plot to get the Coulombic efficiency, not necessarily the molecule itself. It's the collection of that with all these other ingredients. So you can see as a function of iteration, we started with just a kind of a random sampling of these formulation compositions just to be able to initialize the data set. Then we turned on our sequential learning to look at two different methods. In this case, we call them best and uncertainty, but those are basically the two methods I showed before, exploration and exploitation. And the idea was now in an automated way, without a human in the loop, we could find out what is the best within this space that we were mapping out here with our underlying model. What is the best composition to use? And then that's what we were comparing against to other materials. Okay. I think I was targeting 40 minutes. I'm pretty much there. So in summary, these machine learning and artificial methods, artificial intelligence methods can be really transformative, I think. They create these new classes of predictive models. They are, I'm being very clear with this, I don't think they're as good as or will ever replace physical models when available, but where we don't have physical models, I think they are very, very useful for complementing these models within design workflows. They provide this kind of efficient design of experiments approach. This has really been the killer app, if you will, for our commercial customers. And I think within the academic world as well, it's been a really critical for us to be able to produce these kind of this kind of functionality and allow it to be able to be used throughout the university system with all of our collaborators has been pretty great to see. And integrating these tools with new and existing design and modeling workflows is, I think, going to be critical for us in the future. A lot of my proposals, including the one I just wrote with Lon, are working on trying to do just that. So, all right, with that, I'll take a glass of water here and happy to answer any questions. Thank you.
Let's see if we have any questions. No public audience. Yes.
Great talk, thank you. I'm curious if you ever get, like, as you were just saying, physical models that actually are informed from this, because it seems like it's a pretty, a complex recipe, and sometimes the lessons can be very simple at the end. I'm wondering if you have found that along the way.
Yeah, so the answer is yes. I don't have a good slide. I had to delete a lot of the backup slides in order to fit it into this, but this is one example where it kind of led to some new physical insights in the sense of these. I'm not even trying to pronounce the name of these things, but the inclusion of these kind of sulfur bonds within this like benzene chain, it was like a big deal for the Panasonic folks, and they were able to look at that more closely with their DFT to understand like why is this creating the whole mobilities that they were finding that were pretty good. But you kind of touched on a larger problem within the machine learning community called interpretability and the black box problem, right? You want something more than just a model that tells you, this input yields that output. You want to know why it's predicting this output. And we have methods for trying to approach that, to shine some light into it. I don't think any method's going to completely expose the box. I think it's just the nature of the empiricism of this model that it's really hard to do that. But we do have methods for saying, maybe it's I'm going to go to my alloy example because that's where I can explain things. But maybe you can say, okay, for some reason, unbeknownst to the model, but for me, I know why. It's a material science. But for some reason, the model really is correlating chromium content with pinning potential. That is, of all the inputs, and there's a lot of inputs, that is the most important. It accounts for 80% of the variability and variation in my output is chromium content. And it's information like that an expert like yourself can go back and say, okay, I'm going to figure out why that was. Now, for chromium, that's a poor example because we all know why. It forms a scale of chromium oxide on the surface of the steel, and that's why it's able to affect the pinning potential. But what if it said, actually, it's something completely different, like niobium for some reason, and you're like, whoa, niobium doesn't form a scale, but it's having a big effect on corrosion. Why is that? I never saw that before. And that could be an excuse for you to go in and try to understand more about that. But these models are not going to be able to tell you much more than that unless you give it a lot more physics. For instance, we gave this model a bunch of DFT data about cohesive energies or band gaps or something like that. It's possible that it would have said, oh, cohesive energy is a big thing, an important thing that correlates with pinning potential. So, and that would be more help for you to try to understand why that is, because now you've got some more physical insights in that way. But yeah, I think that's an open challenge for the community is how to do that. And the other angle to this is something like PREN is a physical model in a sense that it's entirely empirical, built on years of experience from engineers that they know these particular numbers matter in terms of these physical features matter in terms of corrosion performance. And we can integrate that as well to be able to do a better job of maybe finding better coefficients for the very simple model, the linear model that they were developing, utilizing these kind of machine learning tools. So sometimes there are ways to inform things both directions like that.
Great, thank you. Just another comment though, that the whole mobility, the difference is a factor of 5 there. I noted in one of your earlier.
The whole mobility one, this one?
Yeah, like that's a tremendous boost.
Yeah, it was pretty. I mean, it doesn't look that impressive from here, but most people look at this on a different scale. This is actually was a pretty important discovery for us. So, and they have since experimentally validated this because right now this is all just DFT, but they have validated that, and it was a very interesting, very impactful result for us.
Hello, great talk. I'm kind of similar to the previous question. I'm curious about the error bars you had in like your earlier graph.
Yep.
If everything's a prediction, how do you like know how confident you are in the prediction, or like
So if you want to know the actual math stuff of it, it's all in those papers on the bottom. But at a very high level, so we use random forest models for our machine learning. There's a couple of reasons for that, and for those in the know, I can have a conversation with you afterwards about why. But we have some reasons for that. Part of the reason for that is that you are able to come up with uncertainties, and the source of that uncertainty is basically self-consistency of the prediction. So let's say I have 100 data points and I train the model on 100 data points. I could also try and train the model on 80 points and take 20 out, train on 80. I can take a different 20 out, train on a different set of 80, take another 20 out, a different set of 80, right? I could do that 4 times, right? Or I could do that an infinite number of times. And I get a set of models, right? And how much do those models actually agree with one another? So you're basically looking at, basically from this series of models, how well do they all agree on the prediction of this point in particular? If there's large disagreement because you have a lot of sensitivity from one data point in the training set about the prediction of this particular point there, the pink one that has a huge error bar, then it's going to have a huge error bar, right? So what you're basically looking at is a degree of extrapolation from the training data. And that's really kind of the nature of where these error bars come from.
Okay, cool. Thank you.
Yep. Yep.
I guess this is more for the students in the thinking about their futures. And how did you choose this company? How did you find it? How come you're doing the research? We see a lot of people doing research in universities, but can you tell us a little bit about your path towards this position?
Well, my path is an interesting one. I blame life for it. I did my postdoc at Northwestern, so that implies I was probably going an academic route. I interviewed at a couple places. But then I met somebody. I wanted to stay in the Chicagoland area. I couldn't find an academic job there, so I got a job at a company doing a bunch of still research. I was doing a lot of materials research. I was a lot of simulations and things like that. But I also started doing management stuff. I wrote a lot of government grant proposals, which I didn't get a lot of experience. I would have had to do if I went the academic route, but I ended up liking the pace and the nature of industrial work, but I had never done it before. I had never interned at a company before, so I didn't know that until I actually did it. And then shortly after that, not shortly, a couple of years after that, I met somebody, my partner, and he finished his PhD, went to University of Hawaii for the faculty position, and I was caught in a two-body problem. So I needed to move, and the people who started Citrine were good friends of mine from Northwestern. And I called them up. I said, "Hey, do you need anybody who's doing the kind of things I do?" And they said, "Actually, yes, because we are starting up a group to do exactly what you were doing at your old job, but we're doing it here, this government research stuff." So that was just another excuse, another example of where life just takes you someplace you weren't expecting. And it was great. I mean, I work remotely from Hawaii for a company in the Bay Area, and I love it. And I'm doing a bunch of machine learning stuff now, which I was kind of looking at it before, but it kind of forced me to really dive into it. And I'm glad I did, because now it's become very apropos for everything we're doing. I think it's going to have a large impact on a lot of different areas. And so I guess my advice is, just because life throws you for a loop doesn't necessarily mean it's a bad thing. I think it may knock you out of a local minimum into a more global minimum sometimes. I was very comfortable at my various jobs, my postdoc, my prior job, even my current job in a way. But you just never know. You never know where life's going to take you.
Great talk.
Thank you.
I'm curious to know what thought processes would you like experimental labs to have gone through to like best take advantage of some of the resources that you have and the products that you have? Like, what are there questions that we should be asking ourselves, or kind of like a flow chart to like prime conversation to like take a machine learning approach to a particular optimization problem?
Yeah, I wish I had my backup slides, but the first is going to be a really mundane thing, which is you need to get your data house in order. I think we, as a community, we don't have a good habit of keeping data, and it's not just making sure we have everything in a nice table, but it's also the metadata. Do we understand what all the properties are that impact the measurements we make or the simulations that we do? Do we have all that recorded as well? And it's really when you start to try to do machine learning and you realize what you don't have, and so it's a lot easier to get into the good habit of trying to do that at first. See, I get the audience agrees with me. But then it's actually very similar to, I think, my experience with atomistic simulations. You can leverage machine learning, but you have to ask the right question. It's like, what is the one thing that you really care about? And in this case, for the whole mobility, it was whole mobility. It was one number. And you can do multi-objective optimization, but it's a lot easier if you can distill everything down to one thing or one physical quantity, right? It's not just, you want to make pinning potential high. That's one thing you could do. But as I said earlier, I know as a material scientist that it's all about the stability of a passive film on the surface. And so I could recast the problem to be something more physical, and that's probably an easier problem for you to solve. So very often we're having conversations with our customers in the first couple of weeks. It's understanding the problem and helping. I mean, they know the problem. We're not helping them understand it. We're helping them just maybe distill it down to its most fundamental thing so that we have a much higher chance of actually solving the problem with these tools. Otherwise, you're just throwing a bunch of stuff and hoping something sticks. That's not really the best way to use this, because then you can imagine that the machine learning models will just flail a bit if there's way too much freedom for them. Especially in our field, we have a small data problem, not a big data problem. So we can't expect machine learning models to learn the periodic table. So we have to give as much physical information. We have to give them enough insight. We got to simplify the problem down to its bare minimum, and then you could really see the power of this stuff work really well.
And I want to add to that, like machine learning, I see pretty powerful is because we have a lot of a student here, probably they haven't used like machine learning as I see you can see like machine learning probably on the low level will be like your more advanced Excel spreadsheet, right? Most of the time you collect a lot of data from your experiments and then you put in the Excel and it's okay. Sometimes to give you a nice figure, sometimes give you very ugly figures. And so
or just add a trend line. There's a machine learning model. Yeah.
The machine learning actually can help you to analyze the data. Right, spreadsheet would just help you to finding the fitting parameter, right, the fitting figures. But machine learning can help you find out some hidden correlations, and even human being hardly identified. Okay, so this is I think probably the intro level,
yeah.
Right? Another one is just all those fancy case studies, and like Jim just showed us, is to help you to find out some data point actually you haven't found. Right, from your experiment, some hidden subgroup, and maybe that is a target, right, material, and you want to find, but machine learning can help you to find that, and also generate some new material, and maybe you haven't thought of. So this will be another level. Yeah. So probably we have a couple minutes. Because you mentioned some teaching modules, and Citrix actually is developing. So we have some course instructor here. Do you think? Is this like you have some example to quickly show what kind of some modules, and then the course instructor can quickly, easily adapt it to their courses and to guide students, or like teach to demonstrate to them how can we use a machine learning to analyze data?
Yeah, I mean, so I don't have any slides for this here, but the idea is if at the undergraduate level, well, let me take a step back. When we talk to customers, a big challenge with our customers is that with their employees, the people who are going to use our software, there's a lack of data literacy. Understanding things like data bias, how to deal with materials data sets, how to understand outliers and doing outlier detection, those kind of things. The concept of that. We have to do trainings for them for that. And so we have a lot of experience in the kind of things we think people ought to know if they're going into the workforce. Who aren't material scientists, materials informatics experts, but here are things they ought to know generally about it. So we've kind of built that into course modules that utilize our software so that you can teach this kind of stuff across a variety of different problems, like structural materials. The corrosion example I gave is in there, concrete design, polymer design, things like that. And the concept is we developed this tool set that I'm showing screenshots of here, web-based GUI, to enable people who aren't materials informatics experts and data scientists to do those kind of things. Because we're basically trying to simplify it and put up guardrails to make it easy to do. And we realized that's like pretty similar to what probably an undergraduate course could look like as well, where maybe you don't necessarily need to learn how to use Python and Jupyter Notebooks and scikit-learn. You could do with like a 2-week course utilizing some of our demos and case studies within a web-based GUI to understand the concepts of how do you measure the performance of a model? How do you identify bias in your data set and your model, things like that. And I think that could be pretty relevant for a variety of different courses within the undergraduate level, or even maybe a design course. So we're looking into that. We're exploring that. And yeah, if there's any opportunities here for using some of that, I'd be happy to talk about it.
Course instructor interested, like incorporated the machine learning in your course, and then those are something modules, and you can look at and go find James.
Yep.
Okay, I think that's it. Thank you very much.
Yeah, thank you.
Thank you, James.
Thank you.